Let's go back to making our pizzas. So we know that we have our recipe. But what would happen if we have different amounts of ingredients? So let's say we have 4 crusts, 15 ounces of tomato sauce, 10 cups of cheese. How many pizzas can we make? Well, we need to look at each of the ingredients to determine how many pizzas. If we have 4 crusts, we can make 4 pizzas. If we have 15 ounces of sauce, we can make 3. And if we have 10 cups of cheese, we can make 5. So the maximum amount of pizzas that we can make is 3 because all of the sauce gets used up. So our sauce would be our limiting ingredient. So just like the sauce limits the amount of pizzas we can make, in chemical reactions we call this the limiting reactant, or sometimes limiting reagent. It means the same thing. The maximum amount of pizzas that we can make depends on our starting materials or our ingredients. And so we can calculate the maximum amount using our starting ingredients, and that tells us our theoretical yield. It also tells us how much of the other ingredients that are going to get used, because we are going to have some of our ingredients left over. In a chemical reaction, we might have some of our starting materials left over. So let's look at our limiting and excess reactants in the combustion of methane. If we have 5 molecules of methane and 8 molecules of oxygen, which one is going to get used up first? Well, we're going to do the same thing that we did with our pizzas. We're going to look at, using our starting ingredients, how much of the product we can make. And it doesn't matter which product you look at, just so that you're looking at the same product for both of the reactants. So if we start with 5 molecules of methane, we can make 5 molecules of carbon dioxide. If we start with 8 molecules of oxygen, use our molar ratio, or the coefficients in our balanced chemical reaction. Again, we're looking at carbon dioxide as the product. We can only make 4 molecules of carbon dioxide. So this means that the oxygen is our limiting reactant. The methane will be our excess reactant. Since we make the smallest amount of carbon dioxide, the oxygen gets used up first, and it limits our reaction. Your turn. Try to see how many moles of silicon nitride can be made from 1.2 moles of silicon and 1 mole of nitrogen. Pause the video and determine the number of moles. Well, let's start with our silicon. 1.20 moles. We look at our balanced chemical reaction, so it takes 3 moles of the silicon to make 1 mole of our product. So we can only make 0.4 moles. Well, let's look at the nitrogen now. If we start with 1 mole of nitrogen, takes 2 moles of nitrogen to make 1 mole of our product. And so 0.5 moles we can make. So this tells us that the silicon will get used up first. It is our limiting reactant, and the maximum amount we can make is 0.4 moles. Now note, it is not the reactant that had the smallest amount to start with. It depends on the product, how much product you can make. So whenever you see amounts of 2 different or more than 1 amount of reactant, you want to think limiting reagent problem. You have to figure out which one will get used up first. Now let's assume that we're making pizzas and maybe we burned a pizza or dropped one on the floor or something happened that one of them was not edible. So the amount of pizzas that we made that could actually be consumed, that would be our actual yield. And we can determine how good we are at making pizzas by calculating the percentage of the maximum pizzas that we could actually make. And this is what we call the percent yield. And typically, this is a very highly studied part of chemistry, is increasing the percent yield, because the more product and the more efficiently we can make that product, the more profitable it can be. So if we wanted to find our percent yield, it's actual yield divided by theoretical times 100. So for our pizzas, if we made 2 pizzas that were edible and we could make a maximum of 3, our percent yield would be 67%. Now, can we make something more than 100%? Well, we would be making or producing matter, but in a chemical or in a laboratory setting, it is possible that either we have starting materials left over that didn't get converted into product, or there's something contaminating our product, or it's wet. There's some things that lead to there being a higher percentage than 100%, but this is has to do with types of error that make it so that it would be higher than 100%. So let's look at an example. Let's say that we're going to look at a more industrial setting. So we want to take 28.6 kilograms of carbon and react it with titanium 4 oxide. And when we do that reaction, we get 42.8 kilograms of titanium that is produced. We want to find the limiting reactant, the theoretical yield, and the percent yield. Our chemical reaction is titanium 4 oxide plus 2 carbons gives us titanium plus 2 carbon dioxide. So we're going to start by using the amounts of our starting materials. So our 28.6 kilograms of carbon and our 88.2 kilograms of our titanium 4 oxide. Now I do these problems kind of in parallel because we do follow similar steps. So we have to convert from kilograms into grams. So kilograms are larger, takes more grams to make a kilogram. We have to convert from grams into moles. So we're on our top problem, we have grams of carbon. So I use the molar mass of carbon. And in the bottom problem, we need the molar mass of our titanium 4 oxide. So we'd have to add up the mass of the titanium plus 2 oxygen. Now we go to our balanced chemical reaction. We look at the coefficients in front of our balanced chemical reaction. We see that it takes 2 moles of carbon to make 1 mole. The titanium of just titanium. And for our titanium 4 oxide, it's 1 mole titanium 4 oxide to make 1 mole of titanium. Now we have to go back to grams, because the amount that we were told for our actual yield which was given in the problem, was in kilograms. So we want to go from moles into kilograms. And we can look at the periodic table. You see 1 mole of titanium. It's 47.87 grams. And it's the same for both problems because we want to look at the same product so we can compare. All right, and now because our actual yield was given in kilograms, we're going to convert to kilograms. And we can see that we get, I'm rounding for significant figures, but 57.0 kilograms of titanium. If we start with 28.6 kilograms of carbon. And if we start with 88.2 kilograms of titanium 4 oxide, we get 52.9 kilograms of titanium. So this tells us that our limiting reactant is our titanium 4 oxide because we make the smallest amount of product, and that the maximum that we can make is our 52.9 kilograms. So now if we compare this to our actual yield, which was given in the problem, it said we could obtain 42.8 kilograms of titanium. And we know the maximum that we could make is 52.9 kilograms of titanium. Multiply by 100 to put it into a percentage. We get a percent yield of 80.9%. So we know that from this chemical reaction and the yield that we obtained, we had 80.9% recovery of the maximum that we could make. Your turn. See if you can figure out how many grams of nitrogen and the percent yield of nitrogen using the information from the following reaction. So when I look at this problem, I notice that I have amounts of both of the reactants. This tells me that I'm going to have to figure out which one gets used up first. I also notice that I have an amount of the product, which tells me that this is my actual yield. So let's start with our 9.05 grams of ammonia and the 45.2 grams of copper 2 oxide. We want to convert to moles so we can use our balanced chemical reaction. To get to moles, we need our molar mass. So 17.03 grams if we add up the mass of nitrogen plus 3 hydrogen. It's 1 mole of ammonia. And if we look at the copper 2 oxide, 79.55 grams is 1 mole copper 2 oxide. Now that we are in moles, we can look at our balanced chemical reaction. We see that 2 moles of ammonia produces 1 mole of nitrogen. Now we really could pick any product, but because we have information about nitrogen, this is the most reasonable product to calculate. So 2 moles of NH3 to 1 mole of nitrogen, and 3 moles of copper 2 oxide to 1 mole of nitrogen. Now you could go and calculate the grams for each one of these products, but as long as we're in the product, we can stop at this point and see which one we have the least amount of. But if you wanted to calculate the grams and compare grams, that would be perfectly fine as well. So we can see that we have the least amount of nitrogen produced from our copper 2 oxide. So we can use that to calculate our grams of our theoretical yield. We use the molar mass of nitrogen, and it's diatomic, so that means we have to take the mass of nitrogen times 2. I put moles on bottom so that the moles will cancel. And we see that our theoretical yield from our limiting reagent is 5.31 grams of nitrogen. So this is our theoretical yield. So if we want to find percent yield, it's equal to the actual yield divided by theoretical yield times 100. We take our 4.61 grams given to us in the problem, divide by the maximum amount we could make, which is the 5.31 grams, multiply by 100, and our percent yield is 86.8%.